So, Chapter 6 is on bonds. Simply put, bonds are ways that atoms get to 8 valence electrons, or ways that atoms are attracted to other atoms. So, I'm going to write these down. Bonds form between atoms to make compounds. I know, I'm changing my wording. Each one is just another way of trying to get it across in the same way. All right. In addition, bonds can form between individual atoms, or they can form as networks of atoms. Can form between individual atoms or in networks of atoms. Okay. There are 3 different types of bonds that we're going to be talking about. We're going to go ahead and just start with ionic bonds. All right, so what's the key word here in this type of bond? Ion. What is that? A positively or negatively charged atom. Good. All right. So when we talk about an atom giving up electrons or gaining electrons, they're forming ions. And so an ionic bond occurs when an atom of one type, gives up electrons, and an atom of a different type gains them. Up electrons, and an atom of a different type gains them. All right, what gives? Yep. All right, so one atom's given up an electron, one atom's gained an electron. One's become positive, one's become negative. How do those 2 atoms interact? One atom's given up an electron, one atom's gained one. One's become positive, one's become negative. How do those atoms interact? I heard something. They're opposite, therefore what? They attract. Absolutely. We all understand that opposite charges attract. I'm pretty sure that was like a 3rd grade science lesson somewhere. Opposites attract, and therefore that applies here too. So when we've got ions of opposite kinds, electrical forces hold them together. Ions of opposite charges are held together by electrical forces. By electrical forces. Okay. Now, there are a couple terms that we want to toss in here. Specific terms for a positive ion and a negative ion. A cation, or cation, is a positive ion, and an anion is a negative ion. So an atom that has given up an electron is what? A cation. And an atom that has gained an electron is an anion. Okay, good. All right. So if I were to start with an atom like sodium, what is the most common charge of sodium? If you're not sure, take a look on your periodic table. Positive how much? Positive 1. Good. right here. Okay. And if we brought another ion close, let's say chlorine, what charge does chlorine usually get? I heard it. -1. I'm not sure who said it, but good. Okay. So chlorine has a -1. Now, those two should be attracted to each other because opposite charges attract. That's how electrical charges work. Okay. But what if I took another sodium ion? What if I took another sodium ion and put it right here? What would I expect it to do? Go away? What do you think? Any ideas? Say again? Oh, yeah, I'm saying it is positive, yeah. Would it attract to the chlorine? Would it push away? It'll attract because it's still opposite, yeah. And just because another ion is already attracted to an opposite ion doesn't mean that no others can. In fact, these ions can attract as many towards them as they have physical space to fit in by them. And we can actually make entire structures out of these kind of systems. And you'll see I'm kind of making a bit of a checkerboard pattern here. And what we can do is we can form a network of these ions. So a sodium ion isn't necessarily just attracted to one chlorine ion. It may be attracted to many others on different sides of it. And actually, this is something that we see happen very frequently. The compound that I've actually just drawn out here is salt, table salt. So there's a couple of details that we can indicate about table salt that are dependent upon this network structure. First of all, network structures form crystal-like structures or cause crystals to be formed. Form crystals. Anybody ever had salt in the bottom of a container or salt water in the bottom of a container and had the water evaporate? And it leaves that salt like residue on the bottom? Yeah, those are salt crystals. Okay? Even if we just talk about the salt that you have in a salt shaker, yeah, they're very small crystals that come from larger ones that have been smashed up. In addition, these network structures can cause very high melting and boiling temperatures. High melting and boiling temperatures. Anybody ever tried to melt salt? Okay. Well, don't, because it won't work. If you put a whole bunch of salt in like a cooking pan and then turn on the pan, well, let's put it this way. If you tried this with sugar, what would happen? Sugar could melt and caramelize. Okay. But if you try it with salt, instead the salt just gets really hot and pops out of the tray and kind of launches all over the room. It won't melt. It's really difficult to get it to melt. Logan, go ahead and close it. Okay, so we form crystals and we have high melting and boiling temperatures because each one of these is pulling on the other ions and makes it very difficult to separate. Okay. Last piece here, ionic bonds always form between a metal and nonmetal. Always form between metals and nonmetals. Okay. Questions about ionic bonds? All right. Our next type are covalent bonds. A covalent bond is a bond in which atoms share electrons in their valence shells. A bond in which atoms share that's an M, electrons in their valence shell. So if we had a pair of oxygen atoms, how many electrons do oxygen atoms get total? How many electrons does an oxygen atom get? 8. Excellent. So 2 on the first energy level and 6 on the next. 1, 2, 3, 4, 5, 6. And again, 2 here and another 6 on the outer ring. Now, how many more electrons do they need in order to make it to their full set of, or their full valence shell? How many more electrons does each oxygen need to make it to a full valence shell? I heard it. 2. Okay? Each one needs 2. Now, someone in 5th hour kind of described it as a Venn diagram, where I could overlap these, and there'd be some electrons in that overlapping Venn diagram area. I'm not drawing it like that, but you can think of it in that way. So this electron is actually going to be in both valence shells. This electron is going to be in both valence shells. This one's going to be in both. And this one's going to be in both. And what you'll notice is that this one had 6, but now it can also count these 2. And this one had 6, and now it can also count these 2. Yeah?
How do you know which ones will go in both?
For us, it really doesn't matter. So if I'd wanted to pick this one over here and drag it over here, I could have.
So you just have, and then the amount you can tell is where it
8. Yep. We are interested in the amount. We are not going to worry about which one specifically, because that's really tricky and way above the scope of this class. All right, so each one now has 8 valence electrons. Each one now has a full outer shell, and therefore is unreactive past this point. Okay, a molecule like this would be what we would call nonpolar. Nonpolar molecules. Molecules are nonpolar when the atoms are sharing the electrons evenly. And I don't mean they're sharing an even number. I mean that the electrons here spend equal amount of time on this side and on this side. Each atom's pulling on them with the same amount of force. Electrons are shared evenly and are pulled equally by both atoms. Are pulled equally by both atoms. Okay? All right, so if we're talking about nonpolar molecules, what do you feel like is probably also a topic? Polar molecules. So for this one, I'm going to draw out water. Start with oxygen here. It's got its initial 2, and then another 6, 2, 3, 4, 5, 6, and then a couple of hydrogen atoms. How many electrons does hydrogen have? 1. And just like in our previous setup, they're shared between these atoms. So I can show that the one from hydrogen is being shared to the oxygen, and each oxygen is sharing one with the hydrogen. Now, in this case, the electrons are shared probably like you guys share with a younger sibling, where your younger sibling gets whatever it is you're sharing for way more of the time, and you get whatever it is for a brief amount of time. Did I get that right, or is it the other way around for most of you? That's right? Okay. So in this case, the oxygen nucleus is so much bigger than the hydrogen nucleus that it pulls the electrons closer to it. So even though the hydrogen has a full valence shell, it becomes a little bit positive because the electrons are closer to the oxygen atom than they are to the hydrogen. So polar molecules are formed when electrons are not shared evenly. Not shared evenly. Okay? That means that one nucleus has a stronger pull on the electrons than the other. Has a stronger pull. Yep. On electrons than the other. Okay. Questions on covalent bonds? Last piece here. Covalent bonds always form between a pair of nonmetals. Form between nonmetals. All right, so covalent bonds form between nonmetals. What do ionic bonds form between? Metals and nonmetals. So what pairing am I missing? Metals and metals. All right, and conveniently, the bond that forms between metals and other metals is a metallic bond. Okay, a metallic bond forms between metals. Forms between metals. And exists when the valence shells of metals overlap and allow electrons to flow freely. Valence shells of metals overlap and allow electrons to flow freely. What physical property did we just explain? What physical property did we just explain? I heard it. You guys say again? No, not viscosity. Nope, it's not malleability. Right, that's what that is. What one allows electrons to flow freely? Conductivity. Did she say it back there? Okay. All right, so metallic bonds form between metals. Ionic bonds form between a metal and a nonmetal. Covalent bonds form between nonmetals. This is as much as we're going to talk about metallic bonds. Just understand that since the valence shells overlap, they can allow electrons to flow freely. That's what allows them to be conductive. You actually won't learn much more than this, even in terms of like if you take chemistry. This is pretty much it. What I would like you to do right now is go ahead and take that packet that I dropped off at your table earlier today. Now, what you're going to be doing is there's 3 steps to this worksheet. The first step involves identifying each pair of elements and determining what kind of bond they're going to have. Now, we've made this easier because none of these are metallic bonds. So you've got 2 choices. I'm going to give you, let's say, 5 minutes. I'd like you to go through it and just identify if it's an ionic bond or a covalent bond.